Now let's start the third section of the chapter 3. One more important reason for determining the components of a vector is that they are useful in adding and subtracting vectors. In this section, we begin by defining vector addition graphically and then show how the same addition can be performed more concisely and accurately with components. Suppose there's a treasure buried in your backyard and you found a map to locate the treasure. To locate the buried treasure, the map says that you must go to the sycamore tree in the backyard and then march 5 paces north and then 3 paces east and dig there, as in this figure. So to locate the buried treasure, you have to go 5 paces north, and which is in the direction of vector A, and 3 paces to east, which is in the direction of vector B. So if these two displacements are represented by vector A and B, as in this figure, the total displacement from the tree to the treasure should be given by the vector C. So we say that C is equal to the vector sum of vector A and B. So in general, vectors are added graphically according to this following rule. So you have to place the tail of the second vector at the head of the first vector. So in here, the second vector is vector B. So place the tail of the second vector at the head of the first vector A. And then the sum points from the tail of the first vector, which is in the origin, and to the first to the head of the last vector. So the sum points from the tail of the first vector to the head of the last vector. Now to add the vectors A and B, we place the tail of the vector B at the head of the vector A, and then some C vector is pointed in the direction where it is extending from the tail of the vector A to the head of the vector B. Now, what if the instructions to find the treasure were a bit more complicated? 5 paces north, 3 paces east, and 4 paces southeast, for example. So the path from the tree to the treasure would be like that in this figure. So we place the tail of the second vector B at the head of the first vector A, and then place this tail of the third vector C at the head of the second vector B, and then the sum points from the tail of the first vector A to the head of the last vector Z. So now it follows that to add more than 2 vectors, we just keep placing the vectors head to tail, and then draw a vector from the tail of the first vector to the head of the last vector, as in this figure. So therefore in this case, the total displacement, which is indicated by vector D, is the sum of the 3 vectors vector A, B and C. So it is vector D is equal to vector A plus vector B plus vector C. But sometimes it may be necessary to move the corresponding arrows when adding vectors. This is fine as long as you don't change their length or their direction. So now in this figure, C is equal to A plus B. So according to our rule, C is equal to A plus B. By moving the arrow representing B, so that its tail is at the origin, and moving the arrow for vector A so that its tail is at the head of the vector B. We obtain the construction as shown is in this figure B. So from this graph we can also see that vector C is equal to vector B plus vector A. That is, the sum of the vectors is independent of the order in which the vectors are added. So it can be A plus B or B plus A. Now note that C is the diagonal of this parallelogram formed by vector A and B in both cases. So this method of vector addition we called as parallelogram method. Let's see an example now. Suppose that vector A has a magnitude of 5 meter and a direction angle of 60 degree above the x-axis, and that vector B has a magnitude of 4 meter and a direction angle of 20 degrees above the x-axis. Now can you find the sum of these two vectors? So we need to find the sum that meets the length and the direction both. So first of all, it is important to picture the problem. So A in here, A is in the direction of angle 60 degrees from the x-axis, and B is in the direction of angle 20 degrees above the x-axis. Since we need to add these vectors, we place the tail of the second vector at the head of the first vector as in this figure. Now the vector sum, which is C, points from the tail of the first vector to the head of the last vector, which is C. So a graphical way to answer this question is to simply measure the length and the direction of C from the figure. So with a ruler we can find the length, which is approximately 1.75 times the length of the A, which is approximately equal to 8.75 meters. Now similarly, with the protractor we measure the angle theta about 45 degrees above the x-axis. But this graphical method of adding vectors yields approximate results and limited by the accuracy with which the vectors can be drawn and measured. So in contrast, exact results can be obtained by adding A and B in terms of their components. To see how this is done, consider figure A, which shows the components of vector A and vector B. So vector A and vector B, and also it shows the x and y component of those vectors ax, ay, bx, by. And in figure B, it shows the x and y components of the vectors C, cx and cy. Now notice that in here cx is equal to ax plus bx, and cy, which is this length, should be equal to ay plus by. Cx is ax plus bx and cy is ay plus by. Therefore, the magnitude of the vector C is equal to cx square plus cy square over square root. And again the angle theta is equal to tan inverse cy over cx. Therefore, the most precise way to add or subtract vectors is to add or subtract their components. So first we need to find their x and y components and add or subtract to find the resultant vector. So the rule of thumb for adding and subtracting vector is, first find the components for each vector and then add the x and y components separately and find the resultant vector. So let's solve our previous example by using components. So we have vector A, and which has a magnitude of 5 meter above x-axis with an angle of 60 degree, and B magnitude is 4 meter and the direction angle is 20 degree above the x-axis, and we are asked to find the sum of these two vectors. So we are using the vector addition by component method. So first let's find the component of each vector. So the x component is A cos theta, which is cos 60 degree, and we can substitute the values in here. A is 5 meters times cos 60, and we are getting the answer 2.50 meters. And now what is the y component of A? It is A sin theta, and theta is 60 degree here. A is 5 meters sin 60, and the answer is 4.33 meters. Now we need to find the x and y component of vector B as well. So the x component of vector B is Bx is equal to B cos theta, here angle is 20 degree, and vector B is 4.00 meter magnitude, and theta is, sorry, this should be cos 20 degree, and the answer is 3.76 meters. Similarly, the y component of vector B, By, is B sin 20 degree. So it is 4 meter sin 20.0 degree is equal to 1.37 meters. Now we can find the x and y component of the resultant vector C by adding each x and y components of the vector A and B separately. So Cx is Ax plus Bx, which is 2.50 meter plus 3.76 meter. We are getting a value of 6.26 meters. And similarly, the y component of the resultant vector C is equal to Cy is equal to Ay plus By, and we know the y component 4.33 meter, By is 1.37 meter. So the answer is 5.70 meter. Now we can find the magnitude by using Cx square plus Cy square over square root. So this is 6.26 meter square plus 5.70 meter square, and taking the square root, we are getting, this is 75.7 meter square, and it is 8.47 meters. And the direction of the resultant vector, again, it's tan theta is equal to Cy over Cx. Therefore theta is equal to tan inverse Cy over Cx, which is equal to tan inverse Cy is 5.70 meter, x component is 6.26 meter, and it is equal to 42.3 degrees. So that's how we add vectors using components. Let's see one more example. What are the magnitude of vector D? So here we are adding three vectors together. We have to find the magnitude of vector D and the direction angle theta of this net displacement for the treasure hunt. So now we have three vectors in this problem: A, B and C. So before finding the vector D, we need to find all the x and y components of these three vectors. So Ax is equal to A cos 90 degree. Here we can say that the vector A is pointing in y direction, therefore there is his vector A's x component should be 0, and if we substitute the values we are getting it's equal to 0. As y component means the vector A, because vector A is directed in the y direction, so the y component should be equal to vector A. So it is A sine 90 degree, and sine 90 is 1, because of that it is vector A, which has a value of 3.75 meters. Now for vector B, B is directed in the x direction, so the angle is 0, and the value is B cos 0, which is equal to 2.25 meters. So it is just the magnitude of the vector B. So y component of the vector B should be 0. Why? Because it is directed along the x direction. And if we substitute the values, it is B sine 0, and it is 0. Now for vector C, it has both x and y component because it is at an angle 45 degree. So for C, x is C cos, it is a negative angle, so it is minus 45, which is equal to 2.12 meter. And the y component is C sine minus 45 degree, which is equal to minus 2.12 meter. Now we can get the x and y component of the resultant vector by simply adding the x and y component of each vector separately. Therefore, dx is equal to ax plus bx plus cx. Now we can substitute the value. Ax is 0, bx is 2.25 meter, and cx is 2.12 meter. So the answer is 4.37 meter. And the y component of vector D is ay plus by plus cy. Ay is 3.75 meter, by is 0, and cy is minus 2.12 meter. So it is 1.63 meters. Therefore, the magnitude of the vector D is dx square plus dy square, and taking the square root. Here it is 4.37 meter square plus 1.63 meter square, and we take the square root. So the value is 4.66 meters. And now the angle is given by tan theta, which is dy over dx. Therefore theta is tan inverse dy over dx, and it is equal to tan inverse dy is 1.63 meter, dx is 4.37 meters. So the answer is 20.5 degree. So that's the angle of the resultant vector. Now to conclude this section, let's see how to subtract vectors. Suppose we want to determine the vector D, where D is equal to vector A minus vector B. As an example, we will consider the vector A and B that is shown in this figure. So to find the vector D, we start by rewriting the equation for it as follows. So vector D is A plus minus B, which is equal to A minus B. So this means D is the sum of A and minus B. Now the negative of a vector has a very simple graphical interpretation. So the negative of a vector is represented by an arrow of the same length as the original vector but pointing in the opposite direction. For example, for B, it should be pointing in the opposite direction and with the same angle. This angle should be 20 degrees. So therefore, to subtract vector B from vector A, we simply have to reverse the direction of B and then add it to A. So this is indicated in figure B. So if when we reverse the vector B, we are getting vector B in this direction. Now what is the vector D? So now it is vector A plus negative value of the vector B. So in terms of components, you subtract vectors by simply subtracting the component. For example, if we consider this subtraction, the components of D are given by subtracting the components of B from the components of A. So dx is equal to ax minus bx and dy is equal to ay minus by. So once we find the components, its magnitude and direction can be calculated as usual. Let's see a simple example of subtracting vectors. For the vectors A and B shown in this figure, we are asked to find the components of D, which is equal to A minus B, and find D and theta for the vector in part 1. Now we know the magnitude of A and B and the direction angles. A is 5 meter, B is 4 meters, theta 1 is 60 and theta 2 is 20 degrees. So all these values are given. Now to find vector D, we need to find the x and y component of vector A and B. So the x component of vector A is simply the ax cos theta, and here the theta is 60 degree. So the value, if we substitute the value, we are getting 5 meter times cos 60 degree, which is equal to 2.50 meters. And the y component of vector A is a sine 60, so 5 meter times sine 60 degree, which is equal to 4.33 meters. Now again we need to find the x and y component of vector B. So x is again b cos theta 2, which is vector B is 4 meters, and cos 20 degree, which is equal to 3.76 meter. And again the y component of vector B is b sine 20 degree, which is 4 meter sine 20, and the value is 1.37 meter. Now dx, the x component of the resultant vector, should be ax minus bx, and therefore it is 2.50 meters minus 3.76 meters. So we are getting a negative value, which is 1.26 meters. And the y component of the resultant vector dy is ay minus by. So it is 4.33 meters minus 1.37 meters, and it is a positive value, 2.96 meters. And we can, if we think about the direction of the vector D, it is in the second quadrant. So we know if it is in the second quadrant, its x component is negative and y component is positive. So it is as we expected. Now we can find the magnitude of the resultant vector D if we know the x and y components. So it is D is equal to dx square plus dy square, and take in the square root value. So which is minus 1.26 meter square plus 2.96 meter square, and then we take the square root. So this is equal to 3.22 meters. And again the angle theta, tan theta is dy over dx, and theta is tan inverse dy over dx, and it is tan inverse dy is 2.96 meters, dx is minus 1.26 meter. So by solving we are getting value 66.9 degree. And now this angle is not correct, and we know that it is in the second quadrant. So we have to add 180 degree to the answer. So the answer is 1113 degree. And in the figure, this figure, we see that the vector D is shorter than vector B, which has a magnitude of 4 meter, and its direction is somewhat greater than 90 degree, as we say it is in the second quadrant, and it is agreed with our numerical results. So this ends our third section of chapter 3. Please be familiar with the adding and subtracting vector examples, and we will go to the next section in our next video.